Okay. Good afternoon, everyone. Welcome to 2022 Mildred Dresselhaus Lecture. As you all may know, this lecture is organized annually in memory of Professor Dresselhaus and in recognition and celebration of a great scientist and engineer whose impact and leadership echoes those of Millie's herself. So it is my great pleasure to be able to introduce the 2022 Mildred Dresselhaus Lecturer, Professor Pablo Hurrillo Herrero. So Pablo is the Cecil and Ida Green Professor of Physics at MIT. Amongst a long, long list of scientific accomplishments and contributions is his groundbreaking discovery of correlated phases and superconductivity in magic-angle twisted bilayer graphene, and the development of the field of Moiré quantum matter and twistronics. Pablo completed his undergraduate studies at the University of Valencia in Spain, followed which he completed his master's degree for 2 years at UC San Diego. Then he left to Delft University of Technology for his PhD and a short postdoc, and in 2008 started at MIT Department of Physics as a faculty member. Pablo has been recipient of, again, many, many awards and recognitions, so time only allows me to highlight a few of them here. Pablo was elected APS Fellow in 2018, Fellow of the Quantum Materials Program of the Canadian Institute for Advanced Research in 2019, and the Member at Large of the APS Division of Condensed Matter Physics in 2019. Pablo received the APS 2020 Oliver Bockley Condensed Matter Physics Prize, the 2020 Wolf Prize in Physics, the 2020 Medal of the Spanish Royal Physics Society, the 2021 Max Planck Humboldt Research Award, and the 2021 U.S. National Academy of Sciences Award for Scientific Discovery. Pablo became elected to the U.S. National Academy of Sciences in 2022. So it is with great pleasure to be able to have Pablo here with us today as the recipient of the 2022 Mildred Dresselhaus Lectureship. Pablo, thank you for your time, and we're very excited to hear your lecture.
Thank you very much, Farnaz and Vladimir and the whole committee for selecting me for this lecture. I'm a great fan of Millie Dresselhaus, as you will see, and it's really a great honor. I really feel humbled by being selected. Now, I'm going to tell you about magic of Moiré quantum matter, but before I start, I want to tell you a little bit about the deep influence that Millie Dresselhaus had in my life, my scientific career, and you know, everything. So my first literary encounter with Millie was in Delft in 2001. And so Delft is this little town in the Netherlands, full of channels, really pretty, bucolic, very small. It's there for those of you that, just about an hour south of Amsterdam. And I was there in 2001, and I looked more or less like this. And I was thinking, they're like daydreaming, okay, what should I do for my PhD, okay? So I was in my office, and then I came across this book, The Science of Fullerenes and Carbon Nanotubes, written by Millie Dresselhaus, together with Jean and with Peter Enklund. And it was an amazing thing, okay? It's kind of interesting that you have a fullerene and graphene here, no carbon nanotube, but actually the whole book is mostly about carbon nanotubes. And I found this system so fascinating that I decided to do my PhD studying carbon nanotubes. And then, I already knew, of course, of Millie because of the book, but then I kept going to conferences and I kept hearing about Millie and Millie Dresselhaus and this wonderful woman and so on and so forth. I finally met her in 2003 in Korea, and it was great, but I could only speak very briefly with her. Now, what I couldn't imagine back then when I started reading Millie's book is that about a decade later, okay, I would be actually co-hosting together with many friends here, Thomas and Jean and Laura and Deb and others, Millie's 80th birthday party at MIT, right? I never imagined that I would be a colleague of Millie. And her office was just upstairs of my office. I'm on the second floor of Building 13, very close to here. And she was just on the third floor, kind of right above me. So I would always be sitting there and thinking, what would Millie do in this case? And I would literally almost like I could see her, So, so this was really something that I enjoyed a lot, this party. There were so many people coming from so many places around the world. Now, Millie, is an extremely distinguished, was an extremely distinguished scientist, okay? You know how, I don't know, my family sends me these WhatsApp videos, funny videos, and there's one where the Queen of England, meets all the presidents of the US. This is Millie's version of it, she has earned so many awards and medals and distinctions. You can see that for decades she kept, going to the White House to meet all the various presidents, No wonder she's called the Queen of Carbon, So this was, I think, for the National Medal of Science. This is for the Lawrence Award. This was for the Presidential Medal of Freedom. And she really has had such a big impact in science that it is really hard to overstate this. But not only that, okay, she is also extremely well known as being, a great supporter of women in science. This is another picture of Millie that I really like. This is from the Kavli Nanoscience Prize ceremony in Oslo. But a picture that I like even more than this is actually this one. I don't know how many of you know, but there is an award. Millie donated her, her entire prize from the Kavli Foundation to establish an award at MIT, the Dresselhaus Award to support young women faculty. And this is Paulina. I don't know if she's in the audience or in Zoom, but she was the inaugural recipient of this Dresselhaus Award at MIT back when she was an assistant professor. So,
Could we perhaps turn the lighting down so the contrast will show up better on the screen?
The rest of the slides pretty much are white, so don't worry so much. Yeah, I wish it was before. So now Millie has mentored and inspired, many, many generations of students. And I know that, when Anantha Chandrakasan, started this series of Rising Stars in Electrical Engineering, I know this is an event that, Millie really enjoyed. Many women would come to MIT to discuss about academic careers. It's an academic career workshop. She would frequently give advice to these young women. You can see here this is the batch of the Rising Stars. I think this was in 2015. And in fact, both Millie and Anantha provided great inspiration for our own physics department to start also a Rising Stars in Physics series, okay, where we invite also a cohort of senior grad students and women postdocs to come to MIT. This is the inaugural one in 2016, and then we've been doing it since, for many years now. The last one was at Princeton. I always go to all of them, and it's really, one more, this is something that Millie, inspired me, to do, and I really thank her for that. Now, I could go on for hours, going and talking about Milli, okay, but I also want to tell you a little bit about, the magic of molecular quantum matter. So I'll just, I'll say, one more word at the end, but let me get started with the lecture itself. So this is a very recent field, okay, that started only a few years ago. But because I know that this is a very broad audience, let me start with, with the following. Let me start by mentioning that among the states of matter in the universe, which are most fascinating, okay, are those where the interaction between the constituent particles that make up that matter are very strong. Yeah? So this is something that happens in all areas of physics and in many areas of science. So one example is the quark gluon plasma. This is a state of matter where quarks and gluons are very strong interacting mix. There's a big soup. This is the type of soup that occurred at the beginning, at the Big Bang, just a few nanoseconds or microseconds after the Big Bang, and that nowadays we can recreate when we collide heavy ions in accelerators, such as the one at Brookhaven National Laboratory. Another very strongly interacting state of matter, a strongly correlated state of matter, is that occurs in nuclear matter in neutron stars. Okay? So neutron star, this is a picture from the Chandra X-ray Observatory of a neutron star there. If you go to Wikipedia, you can see that neutron stars consist of all these layers, which are strongly, made of strongly interacting neutrons. These layers, these different phases are called nuclear pasta, so they have very interesting names. The Bucatini phase, the lasagna phase, the spaghetti phase, The astrophysicists, as usual, they're very good at naming things, very creative. And these are all, again, very strongly interacting phases of matter. Yeah? And perhaps something which is closer to my heart are the different states of topological matter that you can obtain when you take a system of electrons into dimensions and you apply a very large perpendicular magnetic field. Then you enter something called the quantum Hall regime and the fractional quantum Hall regime. And there, the strong interactions between the electrons lead to very unusual properties. For example, the charge of the quasi-particles can become fractionalized, and quasi-particles also acquire very exotic topological properties that make them behave very differently from regular electrons. Yeah? So all of these are just examples of what happens when you have systems of particles which are interacting very strongly. Now let me zoom in a bit more into the field of strongly correlated quantum materials. Yeah? Quantum materials are vast families of materials where the interactions between the electrons play a very dominant role. The most studied family of such materials are the high-temperature cuprate superconductors, where if you take a phase diagram of temperature versus doping, okay, you have all of these phases, okay, including superconductivity, but many others. And despite more than almost 4 decades of intensive theoretical research on this problem, we have very little understanding over most of these phases. Okay? Now, let me just to exemplify, what's the issue with quantum materials? Okay, it turns out strongly interacting systems in general, okay, and quantum materials too, are very hard to solve theoretically. As an example, let's take these high-temperature cuprate superconductors. Okay, all of the action takes place in this plane of oxygen and copper atoms, where if you grow a material, in the stoichiometric, composition, you have 1 electron per copper atom. Okay, this is a system that should be a very good metal, but due to the very strong repulsion between the electrons, the electrons cannot jump from copper atom to copper atom, and they become locked into their positions, and they form something called a correlated insulator, a particular one called a Mott insulator. And now a very interesting thing happens when you remove a few of these electrons. Yeah? Because you have now removed a few of these electrons, now the remaining electrons can actually hop between occupied and empty sites, and they do this in a correlated fashion. In a fashion such that it generates, or it creates, superconductivity. Yeah? And we have no idea exactly how this happens. We believe that the model that describes, this correlated hopping of, pairs of electrons superconducting through your system is due to this gentleman, John Hubbard, okay, which is a model, is the simplest model that people think that describes the essential physics of this problem, where you have a penalty U to doubly occupy, a single site with 2 electrons, and then a hopping energy T, which allows you to hop between occupied and empty sites. And then I said that we believe that this is the model that describes this system because we cannot actually solve this model theoretically. So it is only like we think that it describes the system, but we don't know for sure. Yeah? For any realistic number of electrons, okay, in practice for more than 10 or a few electrons, we cannot solve this model, okay? And we can only just make approximations, and different people do different approximations, et cetera. And basically, there's no agreed upon solid understanding of this problem. This difficulty to solve theoretically these type of problems of strongly interacting quantum systems has led to many alternative approaches to try to investigate the physics of strongly correlated systems. One of the most successful, and one which was largely pioneered here at MIT, is the field of using ultra-cold atoms in optical lattices to investigate the physics of strongly correlated quantum materials. So the atomic physicists can shine lasers at each other, and they create this periodic potential, and they can load this periodic potential with atoms, one atom per side here. And interestingly, they can tune the interaction between these atoms, okay? Such that already about 20 years ago, they were able to tune between a Mott insulator and a superfluid, okay, by using a trick called a Feshbach resonance. But anyway, it doesn't matter too much the name. It's just a trick to tune the interaction between systems. Okay? Now, this was done with atoms which had an integer spin, so they were bosonic atoms, and this is a realization of the Bose-Hubbard model. A few years later, they were able to do this with atoms with half-integer spin, so there was a realization of the Fermi-Hubbard model that was closer to electrons, which have half-integer spin. And just to give you an idea of what is some of the latest, the community now has been investigating anti-ferromagnetism in this Fermi-Hubbard model. Okay? It means that if you load these atoms in this grid, you can see that they alternate spin up, spin down, spin up, spin down, at least over short distances. Okay? So the ultra-cold atoms community is investigating this corner of the phase diagram. Yeah? They would like to investigate the entire phase diagram, and in particular reach this region of D-wave superconductivity or superfluidity in their case, due to repulsive interactions. But this is actually very hard to do technically. They have to cool down by 1 or 2 orders of magnitude with respect to the current temperatures that they are at. And they are already at like a nanokelvin or 0.1 nanokelvins, and they still need to go lower in temperature. Yeah? This is not fundamentally, forbidden or anything like that, but it's extremely hard. And, although some progress is being made, it's really a great technical challenge. So we have these two platforms, traditional platforms to investigate quantum materials. On one hand, we have actual materials with lattice scales of the order of an angstrom or a few angstroms. On the other hand, we have cold atoms in optical lattices, where the typical length scale now is of the order of a micron, the separation between these atoms, set by the wavelength of the laser, more or less. And what I want to tell you about today is that as of a few years ago, we have a new platform called Moiré quantum matter, where the typical length scale is the Moiré length or Moiré wavelength, which is of order 10 nanometers. This is very conveniently 2 orders of magnitude from either of these other two platforms, okay? So it's going to be a complementary platform in many aspects to these other two platforms to investigate strongly correlated and topological physics. Associated with these length scales are temperatures or energy scales. So in the case of quantum materials, typical, temperature scales are 100 to 1,000 Kelvin for these strongly interacting systems. For cold atoms, 0.1 to 1 nanokelvin. In the case of Moiré quantum matter, it's about 1 to 10 Kelvin, the typical temperature scale, which is a very convenient temperature scale to investigate in a solid-state physics laboratory. Now, initially, the development that enabled the study of this Moiré quantum platform was this. Sometimes it's called twistronics, okay? Which is the fact that we can do with two-dimensional materials something that was impossible to do in the history of material science. Yeah? We can place two-dimensional crystals on top of each other with any arbitrary angle of rotation between the two crystalline structures that we want. We can design it and we choose it completely at will. This can be 60 degrees, 27 degrees, 1.1 degrees, I will show you, why not? Any angle that we want. And the properties of the bilayer can be dramatically different from the properties of the constituent layers that you started with. Okay? So now, so that you can play a little bit and get a feeling with this, about this, I'm going to pass around this, Moiré simulator, this twistronics simulator, okay? Please bring it back to me at the end. I have two versions, the small and the large one. Both work. And you can play with it a little bit, and then you can get a feeling. Now, let me stop this before you get too dizzy. Over the past few years, using this Moiré quantum matter platform, the amazing thing is that we have been able to realize pretty much all of the phases of condensed matter physics, okay? So we have realized correlated insulators, superconductivity, various topological phases, magnetism, nematicity, ferroelectricity, strange metals, generalized Wigner crystals, excitonic insulators, etc. And all of these phases of matter have been realized using just 2 or 3 simple materials. It's like you can, to some extent, you can eliminate a lot of the complexity of the periodic table and the chemistry, and just with graphene and with a couple other things, you can realize almost all of behaviors which are known in quantum condensed matter physics. So with this introduction, let me tell you what I would like to discuss about today. Okay? I'm going to introduce graphene and magic angle graphene and the discovery, etc. Then I'll tell you about what I call the rise of Moiré quantum matter, the developments that have happened since the initial discovery. A lot of the discussion has been focused on graphene, so I want to spend a few minutes telling you also about Moiré magic beyond graphene, in particular, the discovery of Moiré ferroelectricity in bilayer boron nitride. And then I will end with a little bit of an outlook on what are things which are happening in neighboring communities, because this is actually a field that is expanding well beyond the condensed matter electronics community. So let me get started with this. So graphene is a honeycomb of carbon atoms. All of these atoms are identical from the chemistry point of view. They're all carbon. But from the crystallographic point of view, we have 2 atoms, the A and B atoms, or the red and green balls here. That's because in order to tile a honeycomb, you need a 2-atom basis and 2 unit vectors. So you can calculate the electronic properties of graphene in a very simple quantum mechanical model. And here is the electronic structure, energy versus momentum in the plane, in the x and in the y direction. And if you zoom in near the Fermi energy, you have this very unusual energy momentum dispersion, okay? Usually, the kinetic energy of electrons in a system is quadratic, okay? Parabolic. That's what most systems exhibit. But in graphene, it's this linear energy momentum dispersion, which resembles that of photons, okay? Except that electrons are fermions. So this would be something like what neutrinos, the dispersion of neutrinos if they truly had 0 mass. In fact, the equation that describes, and I think this is about the only equation I have in the talk, so don't worry. The equation that describes the behavior of electrons in graphene is the Dirac equation in 2 dimensions for massless particles. Okay? So there are all these analogies of electrons in graphene and ultra-relativistic massless particles that have been studied and explored over the years. And many of the unusual properties of graphene are due to this fact. Now, in the Dirac equation, this is, so that you see energy is linear in momentum k. This thing, alpha and beta, this is a pseudo-spinor that tells you in the Dirac equation whether the spin is up or down, but here it just tells you whether the electron is on the A type of atoms or on the B type of atoms, okay? And then we also have 2 of these valleys, we call them K and K prime, 2 of these Davos Dirac cones. So we say that electrons in graphene have this spin up and down and valley K, K prime degrees of freedom. Now, this is the electronic structure of graphene. What happens if you put graphene on top of graphene and you rotate it, okay? So if you do this in real space, what happens is that you form a Moiré pattern where the Moiré wavelength, which is the distance between the soccer balls that you see here on the screen, okay, roughly goes as 1 over the twist angle for small twist angles. Okay? So now, this is what happens in real space. Okay? Let me show you now what happens in momentum space and therefore what happens to the electronic structure. So this is graphene. This is the Dirac cones of electrons in graphene. This is the electronic structure. This is just a zoom in of this. This is the reciprocal space, the Brillouin zone. And if we have a finite number of electrons in graphene, our Fermi energy would be up here. And this would be the Fermi disks at K prime points, okay, the Fermi surfaces. Now, if we put another graphene sheet on top, yeah, and it's perfectly aligned with the previous one, yeah, then you have both Dirac cones of layer 1 and layer 2 on top of each other. The reciprocal spaces are on top of each other. Everything is aligned, okay? Now, let's twist a little bit, okay? So let's rotate the two graphene sheets in real space, the reciprocal spaces or the momentum spaces also rotate and by the same angle. Okay? That means that the Dirac cones of layer 1 and layer 2 separate, and they separate by a distance in momentum space which is proportional to the sine of half the angle. Okay? So this twisting leads to layer Dirac cones separating in momentum space. Okay? Now, for what I want to show you in a moment, it's good to start with a small twist angle, so that the sine of the angle is the angle. Okay? So let's start with that. So let's imagine we have already two graphene sheets on top of each other, and there's a small twist angle between the two graphene sheets. Okay? Now, the electrons in the two graphene sheets, in layer 1 and layer 2, have this energy momentum dispersion. Okay? And the separation between those Dirac cones is proportional to that small twist angle. This would be the situation that would be realized if electrons in one graphene sheet did not know that the other graphene sheet exists. Okay? However, when we place these two graphene sheets on top of each other, they're only 3 angstroms apart. So the electrons are very much aware that the other graphene sheet exists, and in particular, they can tunnel between the two sheets, back and forth. Okay? That leads to band repulsion, or a gap, an opening of a gap there at the crossing point. Okay? That is the same thing as bonding anti-bonding states in the hydrogen molecule, but now for a giant graphene molecule. Okay? Now, the situation shown here is when this interlayer tunneling is much smaller than the energy of that crossing point. But what happens if I now keep reducing and reducing the twist angle? Yeah? These two Dirac cones get closer and closer and closer to each other, and that crossing point, which pushes one of these bands down in energy, okay, it pushes, because of the band gap opening, pushes one of the bands down in energy, they get closer and closer and closer, and it pushes it to lower, lower, lower energy until it reaches 0. Okay? At that point, okay, we say that a flat band condition has been realized, and occurs when this interlayer tunneling is roughly the same as that energy of that crossing point. This flat band condition is realized at an angle which was coined by Bistritz and McDonald as the magic angle. And it happens to be 1.1 degrees for graphene on top of graphene. Okay? Now, I should mention that there was very interesting theoretical work around the time, also by Suarez-Moret, and experimental work by the group of Yves André at Rutgers, where they did study a little bit the single particle physics aspects of this evolution of the electronic structure. Okay? They had already good indications that there would be this flat band, okay? This electronic structure that would touch 0. Now, this is a cartoon picture. Let me show you an actual calculation. Okay? This is energy versus momentum for magic angle twisted bilayer graphene. These blue bands are the flat bands. You can see that they're not exactly flat. They're not all at 0, but this is much, much flatter and very different from the original Dirac cone that I showed a moment ago. Okay? The velocity of the electrons is orders and many orders of magnitude smaller than the velocity in the original graphene sheets. Okay? Now, if we populate with electrons this flat band, okay, flat in momentum space, yeah, if we now want to see where are those electrons, where do they go in real space, we have to do a Fourier transform to go from momentum space to real space, and the Fourier transform of a very extended flat object is a highly peaked object. Okay? So if you calculate where do the electrons like to be when you place them in this flat band, it turns out they like to accumulate in certain regions in real space where the atoms, these regions we call them of AA stacking, where locally it seems like all of the carbon atoms in one sheet are on top of the other atoms in the other sheet. Okay? In those regions, electrons like to be, and these regions are separated, they're tunnel coupled by regions that we call of AB or BA stacking, where due to the very small twist angle, the carbon atoms go out of registry in between the two sheets, and they are sort of across each other. Okay? Where the A atoms are on top of the B atoms of the other layer, vice versa. So schematically, this is what magic angle graphene looks like. Okay? We have these regions of AA stacking where the electrons like to be, and these are separated by regions of AB and BA stacking where the electrons do not like to be. Okay? In a slightly more realistic schematic, this is what magic angle twisted bilayer graphene looks like. You have these regions of AA stacking shaded in yellow where the electrons like to be. The regions in between the electrons do not like to be. So you can see, and these regions, in yellow are separated by about 13 nanometers. Okay? So you can see how this is going to function now as sort of an analog of those ultra-cold atom lattices. Is the equivalent of a triangular Fermi-Hubbard lattice for our electrons there. Okay? Now, I put many quotes here. First of all, it looks triangular, but it's not triangular. The AB and BA regions are not identical, so it's actually a honeycomb lattice also. And I put in quotes Fermi-Hubbard lattice because it turns out the electronic properties of these flat bands have interesting topological characteristics that prevent a direct mapping to those ultra-cold atom lattices. Okay? The wave functions have very different character. But, sort of, you can think of it as a lattice where we're going to put electrons and we're going to see what happens. Okay? Now, before I show you some data, a lot of people always ask me, like, how do you actually do this thing? How do you put the two graphene sheets on top of each other at 1.1 degree? The emphasis is the 0.1. It's important, actually. So let me tell you how we do this. It's at the same time, simpler and harder than you may think, okay? So the thing that we do is we start with a glass slide which has a sticky polymer, a polymer stack in it. Then we bring a substrate which has hexagonal boron nitride on it. Hexagonal boron nitride is a layered material, ultra flat. For the purpose of this, of the first part of my talk, it's just a high quality dielectric material, insulated material for graphene to sit on top. That's the purpose, okay? So we come with our sticky polymer and we pick up the hexagonal boron nitride from the substrate. Then we bring another substrate which has monolayer graphene sitting on top of it, okay? Hundreds of groups around the world can do this. And then we position our hexagonal boron nitride sort of halfway on top of it, okay? Then we bring the boron nitride down and we tear this half piece of graphene, okay? Now, because these two pieces come from the exact same crystal, even though they're at different heights, they maintain registry in terms of crystallographic alignment. Okay? So from the top, we have the glass slide with the polymer, with the boron nitride and half of the graphene on it. And then we have the substrate with the other half of the graphene underneath. Okay? Now, we can rotate the substrate by any angle that we want. For example, 1.1 degree, why not? And then we can shift this on top and we can stack it, okay? And amazingly, we can do this with a precision that produces this beautiful moire pattern at precisely any angle that we want with very high precision, okay? And the electrons see this periodic potential and they behave, in the way that I described, and I will show you in a moment. Okay? So after we stack it, okay, we pick up the second graphene piece, and from then on, we can just do a standard, e-beam lithography, contacting, and doing, making field effect transistors and all kinds of quantum electronic devices, which is standard and the entire community can do, okay? Now, when you make these type of devices, okay, then the magic sort of starts to happen, and what my group, discovered in 2018 is that when you place electrons, when you make these devices at that particular twist angle of 1.1 degree, and it's important that it's 1.1, it's 1.1 plus minus 0.1 degree. That's the margin of error that you have, roughly, okay? And you charge with electrons this system at a certain charging, okay, or at a certain doping density, in particular, 2 electrons or 2 holes per moire unit cell, so it's a tiny density of electrons. The system, okay, which is made out of 2 pieces of the best conductor in the world, graphene, becomes an insulator, okay, a correlated insulator. That happens only, again, if your twist angle is very close to 1.1 degrees. But moreover, if you start now with that density and you have this insulator, now you add just a fraction, 0.1, 0.2 electrons per molar unit cell, and the system goes from insulator to superconductor, okay? And in fact, it is an electrically tunable superconductor where the critical temperature can be tuned by the amount of density of electrons that you put on it. Really tiny, minute amounts of electrons, you can go between insulators and superconductors, okay? So this, we published in 2018. Now, when my students show me this data, okay, I was immediately shocked, because it reminded me of the hundreds and hundreds of times that I had seen at seminars and talks this type of phase diagrams, okay? This is the phase diagram of the high-temperature cuprate superconductors, okay? For the high-temperature cuprate superconductors, here, this zero doping means 1 electron per copper atom, as I mentioned earlier, okay? So 0 means actually 1. Then let me flip this axis so that they are in the same orientation as this, okay? So if you add 1 electron per copper atom, you have a correlated insulator called a Mott insulator. If you dope with holes, if you remove electrons, you have a superconductor. If you dope with electrons, you have another superconductor. In magic angle graphene, at 2 electrons or 2 holes per mole unit cell, you have a correlated insulator due to strong interactions between your systems, between your electrons. And if you add a few more holes, you have a superconducting dome. If you add electrons, you have another superconducting dome. Now, the obvious similarities, there are also many differences, which I'm not mentioning, okay? So don't think that, the analogy also only goes so far. But one big difference between this and this is that this is actually a theoretical phase diagram. In order to populate this phase diagram with experimental data points, you need to grow thousands and thousands of crystals with different stoichiometry, often different material classes, because not all materials can be grown at all dopings, in order to populate this phase diagram. This is an experimental phase diagram, which is done in one device with a single disorder realization without chemical doping, and it takes me a few seconds to go from here to here and measure this, okay? So as you can imagine, this is something that is, it became, very interesting for many people. Now, let me tell you a little bit about what has happened since the discovery, okay? So we posted this in March 2018. We announced it at the APS March meeting in Los Angeles. And then what I call the theory tsunami came, which is that, this is a short list of the first papers that appear within a few weeks, of us posting our experiment. By now, this list has actually several thousand papers, okay? Everybody became immediately very interested in knowing what is the origin of those correlated insulator states and what is the symmetry, the order parameter of the superconducting state, Plenty of proposals have been proposed, even more. As I said, this list has now several thousand papers. All of the letters of the alphabet have been chosen to propose for the order parameter. You have S, P, D, D plus ID, S plus P plus D, F. Basically anything that you could propose has been proposed. I often joke about the fact that, so I came from working on regular graphene, right? Standard graphene, which is quite simple. And there the angle of disagreement between the theorists is about 20 degrees, more or less. Here in this field of strongly correlated quantum materials is 360 degrees. Theories disagree in all directions. In fact, it's 4 pi. It's in all directions of space. So this, for me, was and is, something very interesting, sociologically, and scientifically to see, all of these properties that have been predicted in different ways and how people can disagree so much with each other. Now, the popular press also became quite interested in all these things, and they started to write all these articles about what's going on with these things and very fancy designs and so on. I wish I knew how to design these things, but no, we don't. So now, more importantly, perhaps, is what has happened experimentally since April. So the paper was published officially in April 2018. Yeah? So the first thing that has happened is that we have reproduced our own results many times, okay? Believe it or not, that doesn't always happen, so it's good when it happens, when you can reproduce yourself, okay? That's very good. We have many more devices. We're starting to map, the critical temperature of optimal doping of these superconductors as a function of the twist angle. It's a new knob, a new control parameter in physics, which didn't exist before, okay? And as you can see, there is a dome, which roughly goes from 1.2 to 1, maybe 0.95 degrees, something like that. Yeah? Now, even better than you reproducing yourself is when others reproduce independently your work. Only then it becomes real science, okay? And since we made our discovery, many groups have completely independently reproduced our results and extended them in very interesting directions, okay? The first 2 papers to reproduce our results, the first one was a collaboration between the group of Corey Dean and Andrea at Columbia University and Andrea Young at UC Santa Barbara. Not only they reproduced our results, they also extended, they showed what happens if you apply pressure Remember that this magic angle condition depends on this interlayer tunneling. So when you apply pressure, you change that tunneling between the electrons. And they were able to make devices at a larger angle, which was not magic, but then you apply pressure, and that angle became magic, okay? And they saw superconductivity, etc. The second paper was by a group of Dimitri Efetov, back then at ICFO in Spain, where he showed that there are additional superconducting domes for some types of devices, okay? Basically, robust superconductivity and correlations, etc., have been reproduced and extended by many, many groups, all over the world, okay? Mostly in the US, but also a few now in Europe and in Asia. Now, we have discovered plenty of other phenomenology which is characteristic of quantum materials in this system. Okay? For example, strange metal behavior, nematicity, Fermi surface constructions, cascades of phase transitions, pseudo-gap physics, etc. Okay? One of the ones that has attracted most attention is this strange metal behavior. Okay? Strange metal is, if you remember, this is the phase diagram of the high-temperature couplet superconductors. Strange metal is this big phase here. Okay? It's called strange metal because the behavior of the electrons is strange. We don't understand it. Okay? So very original name. And in particular, one of the things that happens here for high-temperature couplet superconductors and many other quantum materials is that the resistivity is linear. The resistance is linear in temperature. Usually you expect it to be quadratic at low temperatures, yeah, for Fermi liquids, but it's linear. Yeah? So this is actually resistance versus temperature for magic angle graphene. You can see it's linear until it becomes superconducting. Of course, once it becomes superconducting, it goes to 0. But remember, we can tune everything in these systems, or in particular, we can choose a device with a twist angle such that the superconductivity is tiny, 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 okay? And then, this is a different device with, you can see that the resistivity is linear, 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 until it just becomes superconducting right at 0.5 Kelvin, okay? In fact, this has been extended, this behavior now, down to 40 millikelvin. Magic angle graphene is the second strangest metal by, strangest meaning going linear in temperature until the lowest temperature. There's only another system, a heavy fermion, which has been measured down to even lower temperatures, okay? So this is something, again, that plenty of people are interested in. We have discovered many other correlated systems using these twistronic platforms, okay? So, or this Moiré quantum matter platform. They include ABC trilayer graphene aligned to HBN, magic angle twisted bilayer graphene. We call this twisted bi-bi. It means 2 layers of graphene with 0 angle, another 2 layers with 0 angle, and now we twist them on top of each other with a magic angle, okay? That's also a very interesting magnetic system. We have also transition metal dichalcogenides Moiré systems. There are really, by now, several dozens of these systems, which all exhibit very interesting characteristics in physics. Now, initially, most of the information about the system was coming from quantum electronic transport measurements, resistivity versus various parameters, field effect transistor geometries, etc. But what has happened is that now, lots of local probe studies, okay? People that have tips that can look microscopically what's going on in this Moiré system, they have been investigating the systems. So in particular, the people do scanning tunneling microscopy, scanning nanosquid, scanning single electron transistors, scanning near field optical microscopy, scanning transmission electron microscopy. There is even something called the quantum twisting microscope, okay? So the first ones were the STM people, okay? This thing is, you can make these devices such that they're open-faced, and you can directly go with an STM and look at these Moiré patterns. So in a famous week, in 2019, 3 papers appear back-to-back in Nature, okay, showing the first scanning tunneling microscopy results in magic angle graphene. There was another paper in Nature Physics here. Let me just twist it so that we give it proper credit, okay? And they all showed essentially very similar type of physics. This system is a very strong interacting system, and electrons do very weird things, which they don't do when you investigate regular materials like monolayer graphene, okay? And in particular, all of these systems, they were able to image directly. This is the Moiré pattern, those AA sites, those bright spots, and you can see the atomic lattice underneath it, okay? And they were able to image exactly what happens with the wave functions of the electrons in this system, okay? Which was very interesting. More recently, something which is very amazing and it has caught everyone by surprise is the fact that the group of Shahal Ilani at the Weizmann Institute has built something which they call the quantum twisting microscope. Okay? They have a sort of an STM microscope. It's a tunneling microscope, but where they have one graphene sheet on the tip of the microscope and the other graphene sheet or another 2D material on the other end, and they can put it on top and in situ rotate and measure the electronic properties as they rotate the system. Okay? This is something that is really extraordinary. You can see here some of those bands which are becoming flatter as they are rotating the system, etc. This is only working at room temperature for now, but I believe Shahal Ilani is going to be next Monday here at MIT giving a seminar about this quantum twisting microscope, and I hope he will start showing some low temperature data. We'll see. But this is really extraordinary, and everybody's hyper excited about this development. Okay? Because the ability to tune in situ, we can make a device with any angle that we want. But once the angle is fixed, it's very hard to change. These people are already changing it in situ. Okay? You can imagine that the kind of electronic devices that we could do if we had electronic control over these, at will. So something that perhaps, the most important, thing, the development that happened, after the discovery was when people saw, discover ferromagnetism, anomalous Hall effect, and quantum anomalous Hall physics in these systems, which brings the role of topology front and center into this Moiré quantum matter community. In fact, one of the biggest satisfactions for me personally, from being part of this community, is that the fact that this Moiré quantum matter has meant the merging of several modern condensed matter physics communities, which did not used to talk that closely with each other. On one hand is the 2D van der Waals materials and heterostructure community, people that did graphene like me. Then you have the strongly correlated materials community, people that did cuprates, heavy fermions, pnictides, etc. And then the people that did topological condensed matter physics, quantum Hall, fractional quantum Hall, topological insulators, biselmi metals. All of these three types of physics and systems come together in this Moiré quantum matter. Yeah? In fact, just a few months after our discovery, together with my theory colleague, Senthil, we proposed that there would be all of these topological physics, nearly flat Chern bands in various types of Moiré superlattices with different type of Chern numbers. And just, there was a lot of other theoretical work also at about the same time. And then just a few months later, the group of David Goldhaber-Gordon at Stanford University showed this very large anomalous Hall effect, okay, a finite Hall signal at zero magnetic field. And then 6 months later, the group of Andrea Young at UCSB showed the actual quantized anomalous Hall effect, quantum Hall effect at zero magnetic field in these systems. And in fact, magic angle graphene, in this case, it was aligned to hexagonal boron nitride. You have to do a trick to break the symmetry of those A and B atoms. But this system holds now the world record for the quantum anomalous Hall temperature for any system, okay? Any semiconductor, etc. Now, the other thing that is happening is that we're making what I call the next generation Moiré quantum matter, Moiré Magic 3.0 and beyond, 4.0, 5.02. Okay, so what does that mean? Well, last year, again, papers published back to back. You can see there's a lot of competition in this field. Papers appear in duos, in triples, in quadruples. So the group of Philip Kim and my group in the same week, we reported back to back in Science and Nature the discovery of a new superconductor, magic angle twisted tri-layer graphene. So now it's 3 layers with a different magic angle, okay, which leads to superconductivity. This happens to be actually the strongest superconductor in the world. Okay, what do I mean by that? I mean the following. Usually when physicists compare superconductors, what we do is we compare the critical temperature versus the Fermi temperature, or the density of electrons, okay? For example, conventional superconductors, okay, those that are understood with the weak coupling theory of BCS superconductivity, are typically near this corner. For example, aluminum. Aluminum has a TC of 1 Kelvin. It has a Fermi temperature of 100,000 Kelvin. It has a gigantic density of electrons, okay? The more you go in this direction, towards this purple band, the more exotic your superconductivity becomes, okay? And in fact, in this purple band are all of the unconventional superconductors, the cuprates, the pnictides, the organics, the heavy fermions, they're all here. They have a relatively high critical temperature with a relatively low density of electrons, okay? Magic angle twisted bilayer, in particular tri-layer graphene, are here. The pairing glue that connects electrons and makes them superconduct is the strongest by far for any material, okay? They have similar critical temperatures or higher actually than aluminum with 4 or 5 orders of magnitude less density of electrons, okay? So that's something we do not understand exactly how come that with such a tiny density of electrons, magic angle graphene superconducts so well, okay? And part of the community is trying to see if we can understand that properly so that if we are able to extract the basic physics, the basic ingredients that are responsible for this, perhaps we will be able to engineer those basic principles at regular metallic densities so that critical temperature will be well above room temperature. Okay, that's part of the motivation for a fraction of the community. Now, not only we have found that 3-layer superconduct, but earlier this year, 3 groups again we reported the discovery of superconductivity in magic angle tetralayer and pentalayer graphene. Also, again with different magic angles. You can see the electronic structures here. They all have flat bands, and the different twist angles. You can get superconducting traces. So now we have actually a family of robust Moiré superconductors. Okay, this is something which is very generic, and that will continue to grow, as we keep making more and more devices. Now, in the last few minutes, I want to tell you a little bit beyond something beyond graphene, okay? Because a lot of the focus has been in the commuting graphene, but you can do a lot of magic with things which are not graphene. So let me tell you about ferroelectricity in bilayer boron nitride. So, all of these phases of quantum condensed matter physics that we have shown with Moiré quantum matter, one of the last ones to be discovered was this ferroelectricity, which is a very emblematic phase, of solid-state systems, but which had not been realized yet until last year. So earlier last year, or maybe now a year and a half ago or so, 3 groups, again, all comes, there's intense competition, but 3 groups, my group, but also the group of Moshe Ben Shalom in Tel Aviv, and the Manchester group, we discovered all 3, we posted in the archive the discovery of ferroelectricity in bilayer boron nitride. Now, what do I mean by, how is different this ferroelectricity? In general, ferroelectricity doesn't like 2 dimensions, okay? Many materials which are ferroelectric in 3 dimensions, if you make them 2-dimensional, the ferroelectricity disappears. That happens not only with ferroelectricity, but with any order. Ferromagnetism also doesn't like 2 dimensions, okay? You have a theorem that says that you cannot be ordered in 2 dimensions. Now, the theorem, of course, doesn't work because we have graphene and we have many other things that order in 2 dimensions, but, it imposes restrictions of what, if you can realize order in 2 dimensions. These are, I believe, most, if not all of the 2-dimensional ferroelectric materials, like single atom thick or single unit cell thick materials that we know, or couple unit cells thick. These are materials which can, which are obtained by exfoliating bulk polar crystals. So you have a strong 3D polar crystal, likely ferroelectric. You make it thin, there's a good, there's some chance it will still remain ferroelectric. Well, I want to show you something completely different. I want to make a ferroelectric out of something which is not ferroelectric, in the same way that I made a superconductor out of 2 things which are not superconducting, okay? But you put them together and you make a superconductor. So for that, I'm going to use bulk bilayer boron nitride, right? I'm going to use hexagonal boron nitride. So bulk bilayer hexagonal boron nitride has AA prime stacking. It also has these AB atoms, like graphene, but now they're actually different atoms, boron and nitrogen. That breaking of the symmetry makes it a wide bandgap insulator. And the natural stacking in the bulk is AA prime. Boron and nitrogen alternate on top of each other. The bilayer case is a centrosymmetric material. It's not a ferroelectric, it's not polar, nothing, okay? The natural stacking means that layer number 2 is rotated by 180 degrees on top of layer number 1. Now, let me do the following trick. Since I can take a monolayer, break it into 2 pieces, and stack them at any angle that I want, okay? I'm going to actually stack them at 0 angle rather than 180 degrees. So I take a monolayer of hexagonal boron nitride. Yeah? Then I put here lines to guide your eyes, and then I'm going to break it. I'm going to stack it parallel to itself, okay? Without rotating it 180 degrees like nature likes to do. I just do it 0 degrees. Then what happens is that this system becomes non-centrosymmetric, but it's extremely uncomfortable. The boron atoms don't like to be on top of the boron and the nitrogen on top of the nitrogen. So what the system does is that it switches into one of the following 2 configurations, either AB stacked boron nitride, where the boron sits on top of the nitrogen, or BA stacked boron nitride, where the nitrogen sits on top of the boron. And it turns out these 2 configurations have permanent electric dipole moment and opposite with respect to each other. So if I can somehow switch between these 2 configurations, I make a switchable ferroelectric, okay? And indeed, that's what we did, okay? So we fabricated, parallel stack bilayer boron nitride. It is an insulator. So in my group, since we do electronic transport, what we did to check what is the state of the ferroelectric is we slap on top graphene, and we made something. We then put dual gates, bottom and top gates, and then we make a ferroelectric field effect transistor, where the state of the resistance of the graphene is going to depend on the polarization of the ferroelectric. Okay? So with this, we measure the resistance as a function of the electric field, which we can control with this dual gate geometry. Okay? And we can see that there is a typical resistance peak of graphene. If we go in one direction, if we sweep back in the opposite direction, there's a switch, and there's a hysteresis. Okay? And this hysteresis, as a function of electric field, is smoking gun for ferroelectricity. In fact, we can do this continuously. Okay? And we can see how this resistance peak, as a function of back gate and top gate, switches abruptly when you go from the BA to AB type of stacking. If we now reverse the direction of your electric field, it switches abruptly at a different field. That's the ferroelectricity. Every now and then, we catch a domain wall zapping through our device, and we can see the bistable, contributions from AB and BAs at the same time. Okay? Now, this is for parallel stacking. What happens if we introduce a small twist angle? Okay? If we introduce a small twist angle, then we actually have a moire ferroelectric, or better, anti-ferroelectric system. Okay? Because now you have those ABBA domains similar to graphene, to twisted Vallejo graphene, but now these are domains of opposite electric field, alternating up and down. Okay? And with an electric field, we can increase one type of domain or the other if we reverse the electric field. Okay? And indeed, if we fabricate devices where we have a small angle, like 0.6 degrees in this case, we can see that we change from one type of resistive state to the other, but gradually, rather than abruptly. Okay? Can we actually visualize these moire antiferroelectric domain patterns? We can. And we can use a technique called piezoelectric, vertical piezoelectric force microscopy. And using this technique, we can directly image the up and down electric field domains in the structures. You can just put them on top of each other, and you can see nicely that it aligns with our moire lattice. Okay? These ferroelectrics work at room temperature. It's about the only thing I've done in my lab which works at room temperature. I'm very proud of it. So it's very robust. It's stable. You can cycle these thousands and thousands of times. Okay? You can wait for as long as you want. The ferroelectric state remains. It actually is extremely fast also. I'm not showing the data, but this thing switches faster than a nanosecond, which is very fast by conventional ferroelectric standards. Okay? It's about as good or better than state-of-the-art technologies. So who knows? Maybe this thing one day could be useful for something, and that would be great. Now, this exact same trick, we have hundreds of materials. We have this bipartite lattice, okay? But these bipartite lattices. So the same crystal symmetry engineering trick that we did with boron nitride to obtain ferroelectricity, we can do it with many other materials. And in particular, with the transition metal dichalcogenides, which are semiconductors, okay? They also can get stacked in AB and BA type of stacking, which has opposite electric dipole moments. And in fact, we have realized ferroelectricity using the four most common transition metal dichalcogenides, WSE2, MOSE2, WS2, MOS2. These are work at room temperature. They're all robust, and they are all ferroelectric. Okay? So within a matter of a few, maybe a year and a half, we have essentially doubled the number of two-dimensional ferroelectric materials, but this list can actually be much, much longer because we have many materials with bipartite lattices. Moreover, this ferroelectricity can be engineered in systems that have any order, systems that are also ferromagnetic, or superconductor, or you name it. For example, recently we just posted electrical switching of a moire ferroelectric superconductor, where we can switch due to ferroelectricity between a superconducting state and a resistive state. Okay? Zero resistance, finite resistance, and we can do this at will as many times as we want. Okay? This was by using magic angle graphene. Okay, so the last minute or two, I just want to tell you a little bit about some of the things that are happening in the community. Okay? So as I told you, with this moire quantum matter, we've been able to realize pretty much all of the phases of condensed matter that we know. Okay, maybe a couple missing. They will be found probably soon. This is using graphene, hexagonal boron nitride, transition metal dichalcogenides, just a few very simple materials, two-dimensional materials. But we have hundreds and hundreds of two-dimensional materials, many of which, in their monolayer form already are very exotic, like superconductors, ferroelectrics, magnets and quantum spin liquids. So you can imagine now that thousands of theories around the world are calculating what happens if I put them on top of each other and at this angle, and at this angle, and this angle, and I do this and I do that, okay? So there is really a tremendous amount of work on this. Let me just show you 2 highlights of things that people have predicted. So if you take a monolayer high-temperature Cooper superconductor and you twist it on top of itself, okay? Beyond a certain critical angle, you realize high-temperature topological superconductivity, a very special type of superconductivity, very different from the one which happens in the natural material, okay? You can also take 2-dimensional crystalline magnets, and you put them on top of each other, and you form these things called moiré magnets, where you have special spin textures called moiré skyrmions, and there's a lot of work actually in this. Some of these have been already experimentally realized, actually. And as I said, there is a lot of magic beyond twist electronics, okay? So there is moiré and twisted cold atom lattices. The people who do cold atoms are beginning to actually twist them. They're cold atom lattices. So this was both theoretical work, and recently, this paper just appeared in China, maybe a year ago, okay? Experimental realization of twisted optical lattices and looking at all kinds of effects. You can do this actually with phonons. You can do with classical vibrating plates or with phonons in materials. You can have this moiré and twisted phononics, okay? And people realize magic angle bilayer phononic graphene and things like that, but they mean phonons, not electrons. You can also do moiré and twisted photonics. This is actually perhaps the largest and fastest growing field. With photonic crystals, you can create these moiré lattices where you can slow down tremendously the speed of light, and you can realize all kinds of nonlinear phenomena. There are big community programs now, and all kinds of, many people are actually working on this, and it is very interesting, the kind of physics that is being explored. Even more, it turns out these regions, these AA regions with flat bands, are regions with extremely high density of states. So people have realized that you can do electrochemistry and catalysis, using these moiré systems with very high density of state, which is local, so you can control it locally. Yeah? And last but not least, people think you can even do, moiré gravity. You can twist bilayer graphene and study, physics, which typically you only study in string theory and so on. We'll see, this one, whether it leads to something or not. But this is a serious guy, so there is some hope. So with this, I want to end by, acknowledging my group members. This is something that, for the graphene part, mostly work done by Yuan Cao and also Danielle and Jane. And then with ferroelectricity has been done by Kenji and Shirui, plenty of other collaborators, I want to acknowledge also funding and support. I'm glad that we're beginning to come back in person to do this type of events. This is actually pre-COVID, but we'll try to do one, post-COVID or now with COVID. And the last slide, acknowledgement number 2, are to Millie. This is a quote that I really like from Millie. It says, she was asked once, what would you tell, young people? And she said, follow your interests, get the best available education and training, set your sights high, be persistent, be flexible, keep your options open, accept help when offered, and be prepared to help others. And I really think this summarizes the spirit of Millie, and I want to thank you all for your attention.
Thank you, Pablo, for a very, very inspiring talk. So we're going to have about 10 minutes for a Q&A, and the event is going to be followed by a reception afterwards. Pablo will be available for answering more questions. I'm going to invite Professor Vladimir Vulovic, Director of MIT Nano, to host a Q&A session.
Thank you very much. Pablo, if I can ask you to join me here, so we have a little more relaxing environment. Thank you so much for an amazing talk. That was truly outstandingly inspiring. It does seem that every moment of the day, every month, there is yet another angle to be pursued in the twisted options of the moiré solids. I would like to open up the floor to the audience. And actually, the way we're going to do it is twofold. There is a Pigeonhole. There's a Pigeonhole web address. You can go to pigeonhole.at.
Yeah, it's there.
There we go. Oh, very good. And type MIT Nano, all caps. And you can submit your questions. We'll curate them. I'll get them on this iPad and do my best to relay them. But before we do that, since we do have in-person attendance, and it's a true pleasure to be able to host a hybrid event with so many people attending, I would like to also open the floor right now to the audience here. If you have a question, do raise your hand. We'll come to you with a mic so you can ask it directly. And as you're thinking of what those questions could be, as you're thinking if you want to raise your hand or indeed send us a pigeonhole question, I'm going to start asking questions. It could be just me if you guys don't contribute. So, first question right here. Let's go over that.
Yes. Is this working?
Yes. If you want to just state your name and...
Yeah, Dimitri Antoniadis here at MIT. All this is very interesting. Of course, these new materials are very exciting. Can you tell us something about potential practical applications in the foreseeable future?
Foreseeable depends how good your vision is, but, I think that, from an engineering point of view, magic angle graphene, I would say it's a superconducting field effect transistor. It's a field effect transistor geometry, and you can switch it between superconducting state and insulator state. So while we are having a lot of fun trying to understand the basic physics of it, an engineer could say like, well, this is already something which could be useful for either classical or quantum superconducting electronics. Okay, in fact, recently together with a group of Will Oliver, a couple of years ago, we made the first graphene-based superconducting qubit. That was a hybrid of graphene and aluminum. Aluminum was a superconductor, but the exact same thing can be done just purely on graphene using magic angle graphene, and you could make a magic angle superconducting qubit. This, some of the things that I've mentioned about ferroelectricity, if we were able to fabricate these type of devices at scale, okay, which is a big if, okay? It's not obvious that we can do that, but if we were able to realize these devices at scale, this is already in the first experiment that we have done, and as basic physicists, we're not engineers, it already switches faster than what we can measure and faster than what's out there technologically, state of the art. So if somehow we were able to control this, build it at scale, be able to make billions of these, all identical, et cetera, which is a major engineering challenge, but I don't think there's any fundamental reason why it cannot be done, it's just hard, then this might be actually perhaps useful for applications in photodetection, in memory, in many things. Both the superconducting, the ferroelectric, we also have magnet versions, etc.
Thank you.
If I may add to that question then, on the ferroelectric demonstration, what's the domain size? How small can the memory bit, let's say, be if this is what you choose to do?
Yeah, so we don't know yet what's the minimum feature size that we'll maintain, but because we believe that it is, we actually know quite well that it's based on this sliding on this domain wall. In principle, you can pattern the parallel stack one down to 5 nanometers by 5 nanometers, 10 by 10. It should work, down to very, very small sizes.
And then the question is just how much current would you choose to pass to probe it?
Well, again, you control it with an electric field, the
Yes,
switching,
yes.
okay? The readout of the ferroelectric state, you can do with an in-plane device or with a tunneling geometry. And because tunneling could be with tiny, actually, currents.
It's truly remarkable. One can imagine stacking it. So if you imagine one day there is a 2D materials foundry sitting in MIT Nano, and many of us are engaged in thinking about how to redefine the world. 5-10 years pass. What do we start seeing? Do we have deeper appreciations of the science? Do we have better understanding of how the world is put together, or have we yet invented another set of fields beyond reproducing the expected phenomena?
Mm-hmm. So I think that, that's a very interesting question. I think one thing that is a limitation right now to the community is the fact that, people hear me say like, oh, and this is very simple how we stack it, but everybody's like, looks hard to me actually. So the fact that, there may be, there are 20, 30, 40 groups experimentally that are able to do this, as opposed to thousands, there is a barrier there in terms of how easy is it to make these devices. You really need a lot of training, and it's, it's not as simple as I made it look. It's also not as hard as people imagine, but it's, it's quite hard. So if we were able to have a quantum foundry that would lower the barrier, would automate many of the pieces and the processes that are involved in making these structures reliably, with high reproducibility, all identical, et cetera, I think it would expand vastly both the basic science that we would be able to do, we would be able to explore many, many more combinations. Remember, we have hundreds of these materials. We have to try many angles, many combinations, 1, 2, 3, 4, 5, 6 layers. So we have infinite possibilities. Doing them manually by hand, it's very costly. If we were able to automate these processes with, some colleagues of mine and I, we created this concept of a quantum press. Right now, my students are like medieval monks, making each device is one of a kind. It takes a month, it's beautiful. We measured it for a year, great physics, but one. If we were able to do this with a quantum press so that we would make hundreds of these and all variations and all colors, etc., that I think we would advance very far, both in terms of basic science, but also in terms of possibilities for applications.
I imagine those layer structures that have 3 or 4 sheets of twisted graphene would be particularly easier to make, which also leads me to ask a question. You demonstrated, at least our colleagues at Columbia, demonstrated by applying pressure, you were able to increase the correlation between the layers. I imagine, especially in those stacked structures, that would be an effect that would be very strongly pronounced.
That's right, indeed. If you apply pressure to this sandwich of 6 or 5 layers, you will change the magic angle condition too, and you will be able to make angles which are not magic, etc. So yeah, in fact, I didn't talk about it, but we know now that there is not just one set of magic angles, but it's a magic angle tree. It's a hierarchy of angles. So you can make many, many angles. Each of them has different topological properties, the electronic structure of the systems, etc. It's something which, again, we need a lot of students to study this. A robot would help.
One of the questions that did come through is asking maybe to explain that very first step, which is using the boron nitride sheet to serve as a stiction layer, picking up graphene. In the process, you are counting on the rip in the graphene. How can that be accelerated, improved, more dramatically controlled in some?
Well, in fact, the thing that I described is how we originally did it, how we used to do it as of a couple of years ago. A couple of years ago, one of my students thought that this ripping, this tearing is actually very violent and it creates a lot of strain at the interface, etc. So what we did is we brought a laser and we just, with a laser, cut the graphene into pieces cleanly without any strain and anything. And now we can pick one separately and put it on top of the other without that ripping apart. So we have, we're making small improvements already in the process. And of course, a laser cutting is much easier to implement than a tearing. Yeah.
Fantastic. Let me see a few more questions here.
Everyone in the audience.
Oh, sorry. Let's start with that. Yes.
Cool. Hi, my name's Kate. I'm a graduate student. Thanks for the great talk. I had a question. So you had this lovely kind of microscopy that you showed at some stage with the triangular domains. And I've always been curious when and how it transitions from those lovely triangular domains to the more sinusoidal moire that we might have seen in the part that we pass around.
So in the pictures that I don't know if you refer to the ferroelectricity part or to the STM, the magic angle, which was more smooth.
More the ferroelectricity part.
So the ferroelectricity part, the reason why you see those triangular domains so vividly is because you're measuring opposite electric field polarization, and there is a domain wall there. As you make the angles smaller and smaller and smaller, those triangular domains grow and grow and grow in size, okay? At some point, an interesting relaxation effect takes place where the lattices are no longer kind of rigid on top of each other, but the atoms start to adjust themselves, because now they have a preferred configuration that they would be more comfortable in, which is not that with a small twist angle, and then they start to adjust. So those triangular patterns can get deformed, depending on what is the relaxation process that takes place. In the case of graphene, that magic angle graphene, it's let's say at a magic angle at 1.1 degrees, that STM pictures that I showed kind of a smooth moire pattern. When you go towards smaller and smaller angle, those ABBA domain walls, they do and shrink very narrowly because of relaxation and become sharp triangles. And people have measured that too. And that occurs at 0.5, 0.4 degrees, something like that. So it's a very interesting evolution in terms also of the lattice dynamics and the relaxation and strain. Yeah.
Gotcha. So then there's only AA parts just right at the
There-
apex of that triangle for
No,
like,
you still have AB, BA, and AA parts, but the AA shrink to a
Yeah.
tiny point. It's like a topological defect of which boundaries come out of it, those triangles.
got it. Thanks so much.
Maybe I'll read off some of the questions that just we also received. Can you in situ change the electron density to change the TC and create a temperature sensor at the millikelvin scale, for example?
That's right. So, as I mentioned, magic angular graphene is an electrically tunable superconductor. We can vary the critical temperature by varying the charge density, which is by varying the gate voltage in a nearby gate. It's a field effect transistor geometry. In fact, people have made now, the most sensitive single photon detectors that exist in the world, they're all based on superconducting, ultra-thin superconductors. And people have made the most sensitive of all of them using magic angular graphene because it's the thinnest superconductor. It's also extremely light, so it recovers very fast, actually. So people have made one, I should be careful. The theoretical prediction is that it would be by far the most sensitive. The experimental realization, I don't remember quite if they made it already, demonstrated it or not, but they have made an ultra-sensitive bolometer for single photon detectors based on magic angular graphene.
I guess the thermal mass is very low, so
It's
we can
extremely
easily...
small. It's carbon and it's 2 layers, so it's really, really tiny. Yeah.
It's amazing. So, another question we received, it says, what are the factors you're using to decide what kind of stack you want to create upon so many options?
This is very hard, okay? So we count quite a bit on guidance from theory, okay? For example, the magic angle, the value of the actual value of the angle was predicted. It was not predicted that it would superconduct and do all this magic, but the angle was predicted, and the presence of flat bands. So people then predicted that, our colleagues at Harvard predicted what would be the angles for 3, 4, and 5 layers. So we made devices for 3, 4, 5 layers, and they superconducted. Initially, 3 layers superconducted better than 2, 4 better than 3, but then 5 went down. So we were a bit disappointed. And then, still, we posted the paper in the archive, and then a few weeks later, after we had posted, our theory colleagues called us and said, you know what? Remember the angle we told you for 5 layers? If you include that relaxation that I discussed with you, the angle changes. Instead of 1.95 degrees, it's 1.84 degrees. So we make devices at 1.84 degrees, and then it superconducted better. So, it was actually quite, we don't know if it's a coincidence or if it was real. The prediction was literally that accurate, but we do count on theory guidance. But of course, most of the most fun things that we discovered are because theory had no clue and they wouldn't predict it, right? So we also have to use a little bit of a sense of smell of, there's this area where nobody has explored, or theory says that this should not work, but I don't believe it. Let's go and look at it anyway. And often we find the biggest surprises there.
Wow. It does seem like a remarkable field, both in a way you're forming your structures and then the way you're testing them, and always keeping an eye on the physics of where this might be going. It's remarkable to me that your accuracy of positioning one angle with respect to the other is down to the 0.1 degrees or 0.01
Even better,
degrees.
yeah.
And I guess that is absolutely necessary, the way you're seeing it, in order to be able to get just the right stack structures.
That's right. Nature sometimes helps a little bit. For example, for 3 layers, we have to get 2 angles right. And for 5 layers, 4 angles right. So it turns out nature likes to help. We're very fortunate. And 3 layers, when you put these 2 angles, which are actually the same angle, is theta and minus theta, the lowest energy state for the set of 3 layers likes to have that symmetry. So even if you're a bit off with the angle, the system does and makes the angle right, And so it has actually been easier to make 3, 4, and 5 layer devices than 2 layer devices. We have a higher success yield for this. The other thing I want to mention is that the devices don't have that angle exactly perfectly. There is also disorder. It's called twist angle disorder. In fact, the person that discovered, measured for the first time that twist angle disorder is here, is currently a postdoc here, but he was a grad student at the Weizmann Institute. So what we see is that devices that have very little twist angle disorder exhibit better electronic characteristics, sharply defined superconducting domes, etc. If we make a device which has a bit more of twist angle disorder, then those electronic characteristics get washed out a little bit. So it's very important to reduce and make that twist angle disorder less than 0.1 degrees to see all of these effects. Yeah.
I love the statement you just made, which is the nature helps a little bit.
Yeah.
One more question, yes.
Hi, I'm Pedro, visiting student here. So my question is, what would be your bet if you have to choose another materials other than the one that you spoke that may present a magic angle as this one? Thank you.
Mm-hmm. So graphene is a little bit special in terms of this magic angle, okay, because of the special electronic structure of graphene, that conical electronic structure. Other materials that have also formed Moiré quantum matter, Moiré patterns, and that exhibit strongly correlated phenomena, they don't have a single well-defined angle. There is a range of angles over which behavior, which is typical of strong correlations, occurs. So in some sense, they are simpler. At the same time, those materials have not demonstrated, for example, superconductivity. They have demonstrated other correlated phenomena, but not superconductivity. So there are advantages and disadvantages of graphene. In principle, what you want is the material to be clean enough because the electrons have to see that Moiré structure. So at the angle that you are, if your angle is such that your Moiré pattern is 10 nanometers, the electrons have to be ballistic over those 10 nanometers so that they have to see that structure to form the particular electronic structure that I've shown. If you have another material which is much dirtier, then you will have to choose a smaller angle. If the material is ultra clean, you can, like in the case of graphene, we can make Moiré patterns much longer and still ballistic, and it still sees that electronic structure. So the key, is to choose a material that is clean enough that for the appropriate Moiré pattern that you have in mind, the appropriate angle, okay, it can actually, the electrons can experience that Moiré pattern, and result in an electronic structure that will give you those strongly correlated phenomena or special topological properties. And any material in principle, any two-dimensional crystalline material can do this, but not all the materials are grown nowadays in sufficient quality and crystallinity that it enables this type of physics.
Thank you. Thank you very much.
I'll ask the last question, inspired by one of the questions that is up here, which is, in many ways, you were guided by the numerical simulation of what might happen when you have started doing your initial experiments. But the complexity of what you eventually achieved might be at a point where math itself might need to catch up. Can you utilize your own systems as a way of double-checking the math, or call it inspiring the mathematical
That's right, yeah. I remember the first time I showed our discovery to, it wasn't published yet, but I showed it to one of our cold atoms colleagues. He told me, shoot, you're going to put us out of business, because he was right. Because he immediately saw that this has that appeal of a simulator, similar to what they are building. We can vary these things, vary the correlation, and see what happens. So we may be able to solve the physics, and help the theorists figure out what's going on. Okay, it has a little bit of that flavor. So of course, he was just being also, joking and very generous. It's a complementary platform to all of these other platforms, and let's see if between all of us we can figure out exactly all these systems which are so complex, to analyze theoretically. If we can, give some feedback to the theorists so that they figure things out. Yeah.
Well, that's clearly just one of the many dimensions this field has already opened up. And given the pace of yet another new discovery, I would expect many, many more discoveries are upon us. Pablo, thank you so much for a fantastic talk. Really
Thank you.
I have a very small gift to thank you. It's built in MIT's Glass Lab.
Thank you very much.
Thank you, Pablo.
Thank you. Kind of a
so there's going to be a reception, and Pablo is going to be available at the reception. It's in room 10, building 10, room 105, the Bush room. Please join us if you have time.